Hello students, now let's move on to next theorem. If f belongs to R of alpha 1 and f belongs to R of alpha 2 on closed interval AB, then f belongs to R of alpha 1 plus alpha 2. So here in this theorem, instead of alpha, we are having alpha 1 and alpha 2. Okay, so here it is given f is Riemann-Stieltje integral with respect to these two functions alpha 1 and alpha 2. And now we need to prove f belongs to R of alpha 1 plus alpha 2. See, this alpha 1 plus alpha 2 is another function. So, if f belongs to R of alpha 1 and f belongs to R of alpha 2, we need to prove f belongs to R of alpha 1 plus alpha 2. Okay. And this is all about the first part of the theorem. And now, also we need to prove integral a to b fd of alpha 1 plus alpha 2 is equal to integral a to b fd alpha 1 plus integral a to b fd alpha 2. So this is the second part of the theorem. So now let's get into the proof. Okay. Since f belongs to R of alpha 1 and f belongs to R of alpha 2, by the condition of integrability theorem we have, for given epsilon positive, there exist two partitions P1 and P2 such that u of P1, f, alpha 1 minus L of P1, f, alpha 1 is less than epsilon by 2. And u of P2, f, alpha 2 and L of P2, f, alpha 2 is less than epsilon by 2. Okay, so by using the condition of integrability for f belonging to R of alpha 1, I have this, and for f belonging to R of alpha 2, this. Okay, now let P star be the union of P1 and P2, so that it becomes a common refinement of both P1 as well as P2. Okay, see, and also we know that from the previous theorem, if u of p, f, alpha minus L of p, f, alpha less than epsilon for some partition p and for some epsilon positive, then it holds for every refinement of p on closed interval a, b. That is, u of p star, f, alpha minus L of p star, f, alpha less than epsilon, where p star is the refinement of p. So, in previous theorems, we have learned this u of p star, f, alpha minus L of p star, f, alpha less than or equal to u of p, f, alpha minus L of p, f, alpha. And here, if this difference is less than epsilon, obviously this difference which is less than or equal to this will be less than epsilon. So where here p star is the refinement of p. Okay. And now u of p star, f, alpha 1 minus L of p star, f, alpha 1 is less than epsilon by 2. So we have used this in this way. U of P1, f, alpha 1 minus L of P1, f, alpha 1 less than epsilon by 2. See here, the refinement of P1 is P star. So this holds for P star also. And similarly here, the refinement of P2 is P star. So this inequality holds for P star also. So in that way, we have u of p star, f, alpha 1 minus L of p star, f, alpha 1 less than epsilon by 2 and u of p star, f, alpha 2 minus L of p star, f, alpha 2 less than epsilon by 2. And we'll name this as equation 1. And now let alpha be equal to alpha 1 plus alpha 2. Okay, then u of p star, f, alpha is equal to u of p star, f, alpha 1 plus alpha 2. And As per the definition of upper Riemann sum, u of p star comma f comma alpha 1 plus alpha 2 is equal to capital Mi, where capital Mi is the supremum of f with respect to the partition p star. So capital Mi into delta alpha 1 plus alpha 2 I. So instead of delta alpha I, we are writing alpha 1 plus alpha 2 I. Okay, and that can be written as summation I equal to 1 to n mi delta alpha 1 I plus summation I equal to 1 to n mi delta alpha 2 I. So this can be split like this. Okay, and this is nothing but the definition for upper sum of f with respect to p star and with respect to the function alpha 1. So this is nothing but u of p star comma f comma alpha 1, and this is nothing but u of p star comma f comma alpha 2. So we have u of p star comma f comma alpha equal to u of p star comma f comma alpha 1 plus u of p star comma f comma alpha 2. Similarly, L of p star comma f comma alpha is equal to L of p star comma f comma alpha 1 plus L of p star comma f comma alpha 2. So now subtracting these two equations, I have u of p star comma f comma alpha minus L of p star comma f comma alpha is equal to u of p star comma f comma alpha 1 minus L of p star comma f comma alpha 1 plus u of p star comma f comma alpha 2 minus L of p star comma f comma alpha 2. So this is less than epsilon by 2 plus this is less than epsilon by 2, that is equal to epsilon from equation 1. So at last we have u of p star comma f comma alpha minus L of p star comma f comma alpha less than epsilon. So by the condition of integrability, we have f belongs to R of alpha on closed interval AB. That is, f belongs to R of alpha 1 plus alpha 2, because we have taken this alpha 1 plus alpha 2 as alpha. Okay, so this is all about the first part of the theorem. Now we'll move on to the second part of the theorem. That is to show that integral a to b fd alpha 1 plus alpha 2 is equal to integral a to b fd alpha 1 plus integral a to b fd alpha 2. So here we'll consider now the upper Riemann integral of f d alpha 1 plus alpha 2. So according to the definition of upper Riemann integral, we have infimum of u of p comma f comma alpha 1 plus alpha 2, where this p belongs to partition of closed interval AB. And here this can be written as u of p comma f comma alpha 1 plus u of p comma f comma alpha 2. So infimum of this is nothing but infimum of this plus this. But we know that infimum of a plus b is greater than or equal to infimum of a plus infimum of b. So using this, we can write this is greater than or equal to infimum of u of p comma f comma alpha 1 plus infimum of u of p comma f comma alpha 2. Okay, so but what is infimum of u of p comma f comma alpha 1? That is actually the upper Riemann integral of f with respect to alpha 1. And what is this infimum of u of p comma f comma alpha 2? It is nothing but the upper Riemann integral of f with respect to alpha 2. So here we have this term is greater than or equal to these two terms. Okay, and since f belongs to R of alpha 1 and f belongs to R of alpha 2, also f belongs, see here from the first part of the theorem we have this. Okay, so since f belongs to R of alpha 1 and f belongs to R of alpha 2, we have f belongs to R of alpha 1 plus alpha 2 from the first part of the theorem. Now we have f belongs to R of alpha 1, f belongs to R of alpha 2 and f belongs to R of alpha 1 plus alpha 2 on closed interval AB. So I can use the definition of Riemann integrability here. Okay, if f belongs to R of alpha 1, then I can write this upper integral as integral a to b f d alpha 1. Why? Because if f belongs to R of alpha 1, then upper integral is equal to lower integral is equal to integral a to b f d alpha 1. Similarly, since f belongs to R of alpha 2, upper Riemann integral equal to lower Riemann integral equal to integral a to b f d alpha 2. And same with this integral also. Okay, so here I can write this integral as integral a to b f d alpha 1 plus alpha 2 greater than or equal to integral a to b f d alpha 1 plus integral a to b f d alpha 2. Why? Because f belongs to R of alpha 1, f belongs to R of alpha 2 and R of alpha 1 plus alpha 2 on closed interval AB. Therefore, integral a to b f d alpha 1 plus alpha 2 greater than or equal to integral a to b f d alpha 1 plus integral a to b f d alpha 2. Name this as equation 2. Now we'll consider the lower Riemann integral of f d alpha 1 plus alpha 2, which is equal to supremum of all else. As per the definition of lower Riemann integral, we have this equal to supremum of L of p, f, alpha 1 plus alpha 2, where this p is any partition of a, b, closed interval a, b. And now I can write this as sum of L of p, f, alpha 1 and L of p, f, alpha 2. And by using this one, that is supremum of a plus b is less than or equal to supremum of a plus supremum of b, I can write this as less than or equal to supremum of L of p, f, alpha 1 plus supremum of L of p, f, alpha 2. Okay, and here this is actually the lower Riemann integral of f with respect to alpha 1. And this is nothing but the definition of lower Riemann integral of f with respect to alpha 2. So I have lower integral of f with respect to alpha 1 plus alpha 2 is less than or equal to lower Riemann integral of f with respect to alpha 1 plus lower Riemann integral of f with respect to alpha 2. Okay, and since we know that f belongs to R of alpha 1, R of alpha 2 and R of alpha 1 plus alpha 2, we can write this as integral a to b f d alpha 1 plus alpha 2 as we did earlier, integral a to b f d alpha 1 plus integral a to b f d alpha 2. Why? Because f is Riemann-Stieltje integrable on R of alpha 1, R of alpha 2 and R of alpha 1 plus alpha 2. So here, since f belongs to R of alpha 1, R of alpha 2 and R of alpha 1 plus alpha 2, lower Riemann integrals can be written as integral a to b f d alpha 1 plus alpha 2, integral a to b f d alpha 1, integral a to b f d alpha 2. So here at last we'll get like this and we'll name this equation as 3. Therefore, from 2 and 3, we get integral a to b f d alpha 1 plus alpha 2 equal to integral a to b f d alpha 1 plus integral a to b f d alpha 2. Because from equation 2, we have this is greater than or equal to these two terms. And from equation 3, we have this term is less than or equal to these two terms. So, from 2 and 3 togetherly, we have this term equal to these two terms. And this is all about the second part of the theorem. Thank you.